The research presented today is about the concept of time to danger, which is an alternative to passive safety for the locomotion of a biped robot in a crowd. For a biped robot moving among people, there are two issues. The robot should keep its balance and it should avoid collision with people. On the balance front, the concept of capturability provides the guarantee that the robot can stop in a few footsteps and maintain its balance forever. On the collision front, things are more complicated. Crowds of people mean dynamic and uncertain environments. In such situations, the concept of inevitable collision states shows that absolute safety, in other words no collision ever, is impossible to guarantee. The usual answer to this problem is to settle for a weaker safety level such as passive safety. In other words, if a collision is inevitable, the robot will be at rest. Many robots use passive safety today. Passive safety has a number of advantages, but it is not flawless. It can be a source of collisions when the robot stops and does not leave enough time or space for the people to avoid collision. The purpose of this research is therefore to explore an alternative to passive safety and to investigate whether maximizing the time that the robot has to replan its motion or that a person has to react can yield fewer collisions, and therefore improve safety. To that end, the novel concept of time to danger is introduced. For a future motion of the robot and a person, time to danger is the time where the robot enters the region where the person can potentially be in the future. This region is dangerous because the person will be somewhere inside it. It is a danger zone. In this simple one-dimensional example, a person is moving to the left towards the robot. The robot cannot outpace the person and the collision is inevitable. The gray area is the danger zone. If the robot enforces passive safety, it will follow the blue curve and enter the danger zone with a zero velocity. If this constraint is lifted, the robot can enter the danger zone later by following the green curve, thus increasing the time to danger. To test whether maximizing the time to danger yields less collisions than passive safety, two locomotion strategies are compared. The first one from the literature uses Model Predictive Control and guarantees fall avoidance and passive safety. The second one has been developed in this research. It also uses Model Predictive Control. It guarantees fall avoidance and time to danger maximization. To compare the two locomotion strategies in exactly the same conditions, a blind crowd scenario is used where the robot is the only one that seeks to avoid collisions. The robot walks in a direction opposite to the crowd. 3,600 simulations under different conditions are used to benchmark the two locomotion strategies. The first two criteria considered to evaluate the time to danger maximization strategy are collision count and collision time. The results obtained clearly show that time to danger maximization yields fewer collisions and, as expected, collisions happen later in time. The last criterion considered to evaluate the time to danger maximization strategy is the relative collision velocity between the robot and the people, which is related to the strength of the impact. On the one hand, this strategy opens the possibility for larger relative collision velocities, which is clearly a negative aspect. However, this may be an artifact of the blind crowd assumption. In the real world, people would be aware of the robot and would seek to avoid collisions. On the other hand, more collisions happen with a lesser relative collision velocity, which is a positive aspect. To conclude, this research has demonstrated the interest of the concept of time to danger as a new tool to address motion safety in dynamic and uncertain environments. It is a viable alternative to the passive safety concept. Future works include a careful evaluation of time to danger in reactive, non-blind crowd scenarios.